Funding for this project was provided by Kissel CPB.
Gravity. It's the soul and the spirit of our planets. Every object in the universe experiences gravitational force, an attraction force. Newton's law of gravitation says that the force of gravity is directly proportional to the masses of the two objects and indirectly proportional to the distance between them squared. After careful calculation, scientists figure out that g, the gravitational constant, is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, to equate the force of gravity to its known proportions. Let's talk about little g.
Slow down.
You know from previous chapters that the weight of an object can be more simply written as Fg equals mg. By transitive property, we can set mg equal to gmm over r squared. Simply canceling out the mass of the object in question, we can determine that little g is equal to big G times the mass of the Earth over r squared. Now you know why little g isn't constant on the entire surface of the Earth. At higher elevations, g is less. More than just elevation affects little g, however. Little g is approximately equal to 9.8 meters per second squared. G apparent is the g that we feel. In reality, g varies with your position on the planet. Imagine the Earth as a perfect sphere that rotates at a constant speed. We know that centripetal force, F sub c, is equal to mv squared over r. Imagine Santa Claus standing on the top of the Earth at the North Pole. Here, his weight is equal to the normal force and he is not accelerating. Another way of saying this is that Fg equals Fn. However, if Santa Claus were moved to Egypt, his weight must be greater than the normal force in order to keep a net centripetal force toward the center of the Earth. Therefore, we can say that Fg is greater than Fn. Another way of saying this is that Fg minus Fn is equal to the centripetal force, mv squared over r. Substituting mg equals Fg and mg apparent equals Fn, canceling out the masses, we get the equation that g minus g apparent is equal to v squared over r. Now let's look at gravitational potential energy. Work is defined as the negative change in potential energy. Gravitational potential energy is defined as U equals negative gmm over r, and is 0 at the point an infinite distance from Earth. This means that as an object moves away from the Earth, its potential energy gets less and less negative. Furthermore, if an object moves closer to the Earth, the work done by gravity is positive since the displacement is the same direction as the force. Consider this. How fast would an object have to be moving in order to escape Earth's gravitational force, assuming air resistance is negligible? Escape speed is defined as the speed necessary to escape a planet's gravitational force and stop moving at an infinite distance away. Knowing that at an infinite distance, potential energy is equal to 0, and knowing that the object must stop moving, we can equate Ki plus Ui equal to Kf plus Uf, which equals 0. Substituting in equations that we know from mechanics, we can solve for initial velocity, which is synonymous to escape velocity. Let's talk about another scenario, the orbital speed of a satellite. Think about this. Is orbital speed the same as escape speed? The answer is no. Consider that the satellite moves around in a circular orbit. The gravitational force of a satellite always points to the planet it's revolving around. Recall that centripetal force, F sub c, is necessary to keep circular motion. Equating gravitational force to centripetal force, we get that gmm over r squared is equal to mv squared over r, centripetal force. Do some algebra and you get the orbital speed. Now that we know the velocity, we can find the period of the satellite. Period, capital T, is equal to 2 pi r over v. 2 pi r is the circumference of the orbit, whereas v is the velocity. Substituting in for v gets t equals 2 pi r to the 3/2 over the square root of gm. Let's talk about Kepler's laws. Law 1. All planets orbit in ellipses. An ellipse has an eccentricity that is between 0 and 1, meaning it is not a perfect circle. The point at which the orbit is shortest is called the perigee. The distance along the major axis from the Sun to the orbit is the radius of the perigee. Since it revolves around the Sun, it is known more specifically as the perihelion. The point at which the orbit is longest is called the apogee. The distance along the major axis is called the radius of the apogee, or, as you guessed, the aphelion. Mathematically, RP plus EA equals A, and RA plus RP equals 2A, where E equals eccentricity, 2A is the length of the major axis, and RP and RA are the radius of the apogee and the radius of the perigee. Let's consider instead that the planets moved in a circular orbit, in reality they don't, because they are elliptical. Assuming that the Sun is in the center, given that the Sun is in the center, is now zero. The eccentricity is now zero, is equal to RA, because the eccentricity is zero, RP equals RA, which is also equal to A. Kepler's second law. Equal areas are swept out in equal time. Closer to the Sun, the planet moves at a faster speed but sweeps out an area with a smaller radius. Further from the Sun, the planet moves slower but sweeps out an area with a larger radius. As a result, equal areas are swept out in equal amounts of time. Notice that the area A is equal to the area B. Another way of saying this is that angular momentum is conserved in an orbit. Let's take the example of 2 points on the orbit, the perigee and apogee. Notice that the velocity is perpendicular to the radius at both points. In an elliptical orbit, this is only true at these 2 points. At any point on the orbit, we can use the conservation of energy to calculate the speed of the planet. Recall that angular momentum is conserved and defined as the cross product of r cross mv. This is particularly helpful at the apogee and perigee because r is perpendicular to v, so r cross mv is really just equal to r mv. Simple cancellation shows that RAVA equals RPVP. This is extremely useful because it comes up a lot on the AP test. The period of the planet is t equals 2 pi a to the 3/2 over the square root of g times the mass of the Sun for any planet in our solar system. Notice that the period of a planet is the same as the period of a satellite, with the exception of the mass in the denominator. It is very important to notice that the mass in the equation is the mass of what is being orbited, not what orbits. Lastly, let's talk about the force of gravity inside the Earth. Newton's shell theorem says that if you hypothetically stand on a point beneath the Earth's surface, the uniform shell of matter above you exerts no gravity. This is because the force of gravity of the particles near you directly counteracts the particles on the other side of you. Following this theorem and assuming that density ρ is constant within the Earth, we can define ρ as density, mass over volume. Because the Earth is a sphere, 4/3 pi r cubed can be substituted for volume. Also remember that m must be big M because it's the mass of the Earth and the density of the Earth. Remember that force is equal to gmm over r squared. By substitution, we can equate the force of gravity inside the Earth equal to 4/3 g pi rho m particle times r by simple substitution. The force of gravity is proportional to the distance from the center. Outside the Earth, the force of gravity follows the equation Fg equals g/mm over r squared.
Like
The only reason you watch
your
fun
position
videos is for the bloopers.
On the planet.
your position on the
This is Arthur.
And then I'll go
He's
like this.
stupid. This guy is dumb.